Yeah, and I also want to come back to the field. Like I said, the temperature field is defined all over the space, but the temperature field doesn't have a time component. In the wave here, in this field, there is a time component, and because there is a time component, it means that the shape of the field, because I said like the field is defined all over the place here. What does that mean? It means that the field exists here and the field exists here. But if it's a field, then it means, first of all, it's not a particle. And it means it exists all the way from the source to the target. That's what it means. Now you may wonder, but how, if that's the case, why don't we have an instant localization here on the target? Why does it take some time for a particle in quotation mark, to move from here to over here? And that has to do with the time composition, the time dependency of a field. So it's a wave like this, and that wave has a peak here. If you don't have a time dependency, that means that this is a fixed curve. But if you add a time dependency, you can make that peak move. And it's that moving peak that is a particle. But you have to understand that there is ripples in this field, because it's not like flat all over. There is always small ripples on the field, and that means that what those ripples in that field means is that there is something there that has a potential to create an event. So when we think about the particle being sent out from the source, the peak of the wave there is very high, and it's very low here. And as time goes on, this peak is moving. And when we make an observation of something, it means there was a peak there. That what was the observation means. There was a peak there. We observed a peak in the wave. When we don't do a observation here, there is a peak passing both sides. And those peaks, since they are waves, they will spread out and then interfere with each other. That's what the wave description of quantum mechanics is telling us. And like I said, the time dependency of the wave is moving that peak, and that movement of that peak we associate with a speed. But while there is a large peak here, there can also be a small peak in front and after. And when we make an observation, it is because there was a ripple in the wave there. We can't make an observation if there is no ripple. But if there is a ripple, there is a possibility to make a observation. And the height of that peak is telling us the probability of making an observation. If you now think about, we have a very high peak here and a very small peak here, that means that thing here is moving faster than that thing, because if this peak is moving towards the slits, the smaller peak will come first. And there is a small possibility that we detect that little peak. If it's 0, we won't detect anything. But if there is a little peak there, there is a possibility. If we don't observe it, then there is always the possibility that we detect the higher peak. But now think about it. We actually have 2 slices. And since it's the wave, that wave will pass both slices. And I said it's a probability to detect an event. And since we have 2 slits opened, it means that we have wave passing in both, and that means that if you always detect the particle here, then it cannot be a peak passing from this side here. That's what it means. If you always detect it in this slit, that means there never was a particle here, because you can only particle is a stupid name. If you detect an event here, that means that there was never an event here, and that means there was no peaks here. But the wave description says it's going to be 2 waves that passes here when you try to make a detection, and that means that there is a probability that it may pass here as well. And we could check that by having a detector here as well, so we can detect them in both things. And sometimes you detect this peak, but you don't detect that peak. And if you detect one peak here, it means there was nothing here. And so you have the description says it's a wave when it comes here and becomes detected, and then what it says, if you detect it here, that peak here becomes 0. No chance of anything to be detected here anymore. And if that is 0, then you still have a wave that goes out here. But this is a single wave, and a single wave doesn't interfere with each other. And it just gives some, and that wave will be spread out. The peak, that wave is going to, that thing here is 3-dimensional. Yeah, so you could think about it like having a peak in that direction as well, and that peak is going to is 3-dimensional actually. So think about it as a sphere, and that sphere is going to hit that screen somewhere, and depending on how far away from the center line it is, the peak will be in the middle of the center line and then fall off to the sides in both the X and Y direction. That means that you will have a pattern that is mostly concentrated in the middle like this, and then weaker at the sides. That's how that's how a particle will behave. But the prediction that is made about where that detection will come is based on a wave. So this is what I mean, that even if you make a observation here, it is still a wave description in between here, because the purpose of the wave description is to predict when the next event comes. That's the purpose of the wave description, to make predictions. The second thing about the time component is like since there is small ripples in front and behind, and there is a possibility to detect them. If you don't detect the large here, but the small ripple in front, it's interpreted as a higher speed, because it's time dependent, and this is moving, and this is, since this is in space ahead of this thing, that means it moves faster, and any ripple behind here is moving slower. So the time dependency tells us that there is uncertainty where in space it is as well. Yeah, okay. So when you send it out here, it's not like the position is in this direction. It's also a uncertainty in that direction as well, and as well in that direction. So you get a sphere here. So basically, this entire room it's saying like we don't really know where it is, because there might be a small little ripple up here in the corner of the room, and if we put a detector there, there is a small chance that we detect that little ripple, and that could mean that and we could detect that straight after the thing. You just say like a millisecond or whatever it takes. Like say it goes the speed of the light over here, whatever that time is, let's say it's a millisecond. So that's very high speed. You understand what I'm saying? It's a field. It's defined everywhere in space. Most of the places it is close to zero, and at some place it's a very high peak, and that peak we are associating with an object in space, which most of the time is where we think it would be according to a pre-20th century thinking about persistence of existence. But a very careful explanation of how reality works tells us that we can't make that assumption anymore. We have to make other assumptions of them, or rather we have to drop assumptions. And with that I'm going to end this. Next will be late 20th century view on matter, and I've already started to touch a little bit about it in this here, but for now I'm a little bit tired, so I'm going to stop this.